Hello and welcome to the Build wolfSSL into Secure Enclaves webinar presented by Senior wolfSSL Engineer David Garski. My name is Kristen and I will be moderating. All attendees will be in listen-only mode, but raise your hand if you'd like to ask them directly. There will also be a Q&A session at the end of the presentation. Please remember to follow us on Twitter for all the latest news and events. And now I present David Garski.
Hi everyone, my name is David Garski, and today we're going to talk about secure enclaves, specifically external hardware that's provided by ST, Infineon, and Microchip. The examples we're going to use today. Slides go. Okay, so we're going to briefly talk about wolfSSL. I'm just going to give you an overview, and then we'll go into the secure enclaves and TPM 2.0 modules, and we're going to talk about cryptographic coprocessors, and then show you some real life examples and how to code things and where to find them. And then feel free to ask questions throughout the presentation, but we'll also ask them at the end. So, all right, so a little bit about our history. So back in 2004, our CEO Larry was at MySQL, and they needed a SSL at that time implementation, and there wasn't one out there that matched their GPL v2 model. And so Larry enlisted our CTO, Todd Auska, to write this in a clean room from scratch in C++ originally. And then in 2006, we wrote a C version of our, what's now wolfSSL library. It was called CYASL back then. And in 2014, we went through a name change. It's same company, same ownership, just decided to ramp it up as a company. So during that time between 2006 and 2011, the company was basically the software was baking, right? So it was solidifying into what we have now. So we have 1,000 OEM customers and 17 resale partners, and we secure over 2 billion connections. And I know that seems like a crazy, unimaginable number, but the things we're in, we know that that's true. So, and this is our product portfolio. So our flagship product is obviously wolfSSL, which is a TLS client server, and it utilizes our wolfcrypt library, which provides all the cryptographic algorithms. We have a FIPS component for wolfcrypt, which allows FIPS 140-2 level 1 certification. And we also have an asynchronous option for wolfcrypt, and what that is support for hardware offload to cards like an Intel Quick Assist or Cavium Nitrox, and those are PCIe cards that generally go in servers. And then recently we've added a few other products such as our MQTT client, our wolfSSH client server, and our TPM library. And all of these are lightweight, highly configurable applications. We also have some wrappers for JNI, C#, Python, and JavaScript. And then we have some other frameworks and examples for TLS termination and proxy. We have a wolfSCEP, which is a simple certificate enrollment protocol. And the secure update firmware example is based on MQTT. And then we have a wolfClue, which is our command line utility, and it's actually in our examples repository. And it provides things like, converting certificates from PEM to DIR and encrypting files, things like that. So our software, all of our software is open source, and what that means is you can go download it freely off the internet, GitHub, our website. We are dual licensed, so what that means is the stuff that's freely available is GPL v2, and you can also buy a commercial license if you didn't want to use the GPL. So all of our support is provided direct from engineers. We're a highly engineering focused company. Out of the 29 people working for us, almost 20 are engineers, so gives you an idea. And we also offer consulting services for integration of our libraries to new platforms or adding new features. This is just a list I put together of some of the features that differentiate us, I guess. Not differentiate us, but that's just some of the highlights. So all of our software is written in C, specifically with C89 compliance, which allows for portability. It's highly configurable, so if there's algorithms you don't want, you can turn them off. We support all of the TLS versions, starting from SSL v3 all the way to TLS 1.3. And we are the first commercial company to have TLS 1.3 final in our software, commercial grade. We also support DTLS version 1 and 1.2. We have, I skipped a little there, we have support for a bunch of hardware cryptography, which I'm going to go into more in the next slide. And then we have a few different math library options to optimize for using stack or heap. And then we recently added a single precision math library, which provides highly optimized math operations for specific algorithm and key size. So like RSA 2048-bit has very specific optimized math. And we also have those for x86 and for the ARM. I think it's the ARM v8 with the 32 or 64-bit. And of course, we have all the.
Sorry, David, we do have a question. I'm just trying to unmute here.
Yeah, do you have a question? All right, I'll keep going, assuming everybody can hear me. So we support PEM and DIR certificate formats, including encrypted keys. And then we have the ability to generate certificate signing requests and sign certificates as per the X509 v3 specification. Of course, we have the FIPS. We have NSA Suite B compatibility, which that defines some compliant algorithms along with TLS for cipher suites. And we have PKCS 7 and 12. And then we have quite extensive OpenSSL compatibility layer. We have over 600 APIs. It's growing continually. And we support many different open source projects, including, just to name a few, like Lighty, STunnel, OpenSSH, Nginx, MySQL, HTProxy, and curl. Yeah, Kristen, can you confirm that everybody can hear me okay?
Yeah, I'm sorry.
Okay.
There was someone that was raising their hand, and so I have unmuted them. And if you'd like to ask your question, you just need to unmute yourself on your end, because we've got you unmuted on the platform here.
Okay. I'll just keep going. Okay, so here's a list of some of the algorithms that we support, and some of the recent additions are the SHA-3, the finalist, the AES XTS, which is the cipher stealing. It's used for disk encryption. And some of the more popular progressive ones like Curve and ED 25519 and Cha-Cha 20, Poly 1305. All right. And this is just a list of some of the operating systems we support. I'm not going to read them off. But you get an idea, we have support out of the box for many operating systems, including more. It's just a lot. So I want to go into the hardware support. So these are platforms that we support hardware crypto acceleration, either through assembly or external hardware. So with Intel, we support the AES-NI extensions for speeding up AES, obviously. And then the AVX extensions are speeding up the large math operations. They have 128-bit, 256-bit, math registers you can use. And then of course the RD RAND, RD seed is the hardware source for random numbers. And then the Quick Assist is that PCIe acceleration card that I was talking about earlier, which we support through our wolfCrypt asynchronous software. And then SGX, which is the software guard extensions. I'll talk about that more later too. And then with ST Micro, we support the STM32. There's a series of micros that support the crypto hardware acceleration. That's symmetric AES, SHA-256. And then I'm going to talk more about the ST Safe and ST33 coming up, along with Microchip Atmel at ECC 508A, PIC32 MXMZ, and Infineon Optiga SLB 9670. That's a TPM 2.0 module.
We do have a question. Do you support TI-TIVA crypto acceleration?
I believe we do, but I'm not positive because I didn't do that work. but I believe we do. So we support TI-RTOS and the TIVA-C. And I can find out for sure. You can always send an email to info@wolfSSL.com and we can answer that. The NXP side, we support acceleration of the Coldfire and the Kinetis with the MMC CAU and the LTC, and of course the IMX6 CAM. We recently added support for a Microsoft chip called Azure Sphere, which has this Pluton security module, and it provides ECC key security and ECC hardware operations. And then with Cavium, we support the Nitrox 3.5 and the Octeon MIPS network processor. And with the Nordic Semiconductor, we support their NR51, 52 modules. And we have a bunch of math assembly speedups for ARM, including their ARM v8, Cortex M4, some of the Intel architectures and PowerPC and AVR and MIPS. All right, now to the good stuff. All right, so secure enclaves. So this term is being thrown around and used in a lot of different ways. I'm not sure which one will settle out, but you can also refer to it as a trusted execution environment or a hardware security module or a cryptographic coprocessor. They can be implemented through software or hardware. The ones we're going to talk about today are implemented in hardware outside the processor. And the idea is to separate and protect sensitive code and data and provide a secure area where sensitive data can be stored.
Question, David, does wolfSSL support independent use of AES to encrypt, decrypt the data, not the SSL data?
Of course, yeah. So our wolfcrypt library itself exposes APIs for all of those cryptographic algorithms, including AES and all the other algorithms listed. I think that answers it. All right, and so some of the objectives with secure enclaves are secure key generation. And what that means is generating the key in the device, protecting that private key material such that it can never be compromised, read. And that's the main goal. And then providing a way to secure those keys, certificates, and data. Ideally, it would encrypt communication between its host and the slave or the coprocessor. Another one would be to have a certificate that's signed by a manufacturer that allows you to verify the trust of that device. Another one would be the true random number generation, attack prevention techniques for differential power analysis and side channel, including tamper resistance. And as a benefit, you get reduced host processor, CPU, and memory usage and improved performance. Typically, depends on the architecture. And then unique device identity, either through a unique identifier or just the unique device key pair. All right, some of the use cases for secure enclaves are, of course, TLS, key establishment. So that would be establishing the symmetric key that's used during a TLS session during the handshake. The schemes used for that are usually RSA and Diffie-Hellman or ECC or ECC. And another case would be cryptographic, just strictly offloading RSA and ECC type operations to a coprocessor. And it could be symmetric ones as well, such as AES and SHA-256. Some other use cases would be authentication using like a challenge response where you have a public key and a certificate, but you also want that entity, either the device or the host, to sign it and return a response. And that way you're able to verify that it is in fact that device. And then of course, signature verification. And another one is counters. So these devices all support a way to have an automatically decrementing counter or incrementing counter for use cases like, a limited use. If you read something X amount of times, All right, moving on. So some of the technologies on chip would be ARM Trust Zone, which I'll talk about. I'll talk about all these actually. Intel SGX, Microsoft Azure Sphere, and all Apple A7s later, they have a secure enclave as well. All of these have a way to protect keys and run in a secure way. And then some of the off-chip solutions, which is what we're focusing on today, is like the ECC 508A or the ST safe, and TPM modules like the Infineon or ST parts. And then I put in the Nuvoton. It's interesting that with TPM 2.0, these are pretty much the only 3 manufacturers that support TPM 2.0. And currently, we've only tested with the Infineon and the ST parts. All right, so the ARM trust zone. In a nutshell, it's basically, imagine a physical processor divided into 2 virtual processors, and one is secure and the other is not secure. And there's mechanisms in place to define those interfaces between the 2 and protect the secure side. And then SGX, that technology has been on Intel's 6th gen Skylake processors since 2015. And it basically provides a protected container where software can be sealed, and it's even signed. It provides memory protection through encryption, integrity through code signing, and it protects sensitive operations against outside inspection. And it can also generate enclave specific keys. So you can generate keys inside the SGX. All right, so off-chip TPM 2.0 is a standard that was released in 2013 by the TCG, which is the Trusted Computing Group. And it's had updates since 2016. And it defines very clearly the commands and responses for many types of cryptographic operations. And I'll dive into this a little more. The cryptographic coprocessor, they're designed to be more low-cost additions to existing hardware. The ones we're going over today only support elliptical curve cryptography, and they use I²C, and there's currently no standard between these types of devices. All right, so I'm going to dive into TPM 2.0 modules a bit here. So originally, these were used in x86-based PCs to provide secure boot and protect keys. There seems to be a new trend where these are being used on embedded IoT devices. It's something we're seeing, and I think it maybe will continue to happen. So the way it works is there are 3 key hierarchies: platform, owner, and endorsement. Each of these hierarchies have their own manufacturer-generated seed that's unique to that device, and they have policies associated with each of them. So to generate a key, that hierarchy seed along with a key template is used to generate a key. The key is generated using a key derivation function that's specific to the TPM specification. There's also a null hierarchy, which is used for ephemeral keys. All right, some of the features are that you can securely generate, store, and use the keys. There's non-volatile storage that's secure for keys and data, and they have the counters as well. And there's a hardware random number generator. They have mechanisms in place to prevent dictionary type attacks. There's a neat feature where when you generate a private key, you actually get an encrypted blob back that you can store on your host. And you can load that back onto the TPM very quickly, and only the TPM knows that key. And it's just one of the inherent features. It allows you to do what's called like a quick key swap. Because the TPMs themselves only allow you to have 8 persistent keys, and you can have 3 or 4 temporary keys that are available that can be swapped out in memory. And then these TPM modules, they typically have like a common criteria or FIPS certification. So these are some of the approved algorithms per the TCG specification that can be used. I'll go over in detail which each module supports on the next slide or coming up. Let's see. So we have the Wolf TPM library that supports these modules, and we designed it to be a embeddable, standalone piece of software that's written with very minimal dependencies. So we've implemented all of the TPM 2.0 native APIs for the TCG specification. We also implemented a TIS layer, which is the transport interface layer for SPI and I²C. We have a single IO callback for all the hardware interface. So you take the library, you build it, and you just define one callback for all the hardware interfaces. And out of the box, we have the examples for Raspberry Pi, the STM32 Cube MXHow, and the Atmel ASF, which is their driver framework. And then this has been tested on the ST33 and the SLB, the Infineon SLB 9670. So typically in a Linux environment, when you have, or any environment, when you have a TPM, there's another layer on top of the native APIs called a TSS. And it's a bit complicated and it's a bit bloaty. And so we decided not to implement that layer, instead add our own wrappers. So we have these Wolf TPM2 wrappers that simplify things like creating an RSA or ECC key and then doing something like an encrypt, decrypt, or assign verify. And then we have wrappers also for taking those keys and storing them, or storing certificates or your own data. And out of the box, we have examples for all of these, including the PKCS7, sign verify, and support for sign verify with large data. So you can take and sign, let's say, a large 10 megabyte file, but break it down into 1K chunks or less. It's up to you, but there's a mechanism to do that. And then we have the ability to generate a certificate signing request. And then we have some scripts to sign those. I'll show you those later to create it, like sign it yourself for testing. And then we have TLS client server examples and benchmarking examples. Okay, so here's the hardware. This is just the side-by-side comparison of the two that we've tested with. One is the ST33 and the other is the SLB 9670. So the ST part supports SPI or I2C. Both of them support similar algorithms. There's some differences with the ECC curve supported on the Infineon. I guess it supports only the prime 256 and a BM 256. They all support AES. I guess the ST part supports the 128, 192, and 256-bit keys. So the ST part also has the FIPS 140-2 level 2 certification. It has quite a bit more storage. It's a flash-based device versus the other one is a non-volatile memory type device. And then I managed to gather some power consumption information. These chips can be run at either 1.8 volt or 3.3 volt, and they're pin compatible. And that's something that is defined by the TCG spec as well. All right, moving on. So we did some benchmarks. They're pretty comparable. There's a few outliers, like Infineon has faster key generation. I noticed that the ST part had some faster public RSA operations with OAEP padding. And then overall, it looked like some of the ECC operations were faster on the ST part. Not always true. So they're pretty comparable. All right, so now we're going to go over the two cryptographic coprocessors that I talked about. Just a quick overview. These are dedicated external chips. They both provide security, such as tamper resistance and some other things. And they provide a way to store keys securely, certificates, and data. Very commonly used for embedded IoT devices. They're designed for low power use. The manufacturers have a way to provision the device such that it has a certificate signed by the manufacturer, and they have processes for allowing you to define what those certificates look like as they come out of manufacturing. And as a benefit, you also get reduced flash and RAM requirements on the host, and it typically increases performance. So, all right, so this is a side-by-side comparison of these two parts. The main things to notice here is that the ST-Safe also supports the 3-4-bit curves and brain pool curves. The ST-Safe has the common criteria certification. I couldn't find any associated certifications for the ECC 508. The Atmel part has 16 slots that you can define for key or data use, and the maximum amount of storage you can put is 1.2K in there. The ST-Safe has 2 key slots, the first one being the permanent private key, and then the second one being an ephemeral key that can be used. And then that remaining 6K can be split into whatever purposes you want to store data. And both of them use a form of encryption over the I2C, slightly different. The ST part allows you to load private keys with a key wrapping mechanism, which encrypts it at another layer. And then the ST part also has a dedicated reset line, so you can hold it and reset. They're pretty comparable otherwise. Is there a question? Let's see.
We do. Is there a plan to support ECC 608A?
Yeah, it's actually in motion right now. So the main difference with that part is that it adds AES 128 GCM support, and it adds some cool features for TLS that allow you to compute the PRF and the hash-based key. So basically, the handshake does some stuff to compute a what is it called? Well, the term is PRF and hash-based key derivation function. It actually allows you to speed up TLS 1.2 and 1.3. And technically, we support the latest CryptoAuthLib, which is their library, and it should be supported right now, but we don't support these TLS speedups yet. And we haven't tested it yet. So those parts are on their way, and it's something we're going to do very soon. Okay, next slide. So we also did some benchmarks for these two parts. And I paired it up against just a Cortex M4 running at 120 megahertz using our software version of these routines. And the add ECC 508 was clearly faster by quite a bit, but you still see quite a bit of a performance improvement with the ST safe, which is nice. All right, these are operations per second. I'm going to move on. So I also captured a few performance differences. So for example, the add ECC sped up the TLS handshake time by 5.7. That was compared against a Cortex M0 and DE21. And then with the ST safe, we did some metrics on memory usage, and it reduced it by 46% when using hardware, which is kind of nifty. All right, so now we're going to talk about some real world stuff. So in our wolfSSL and wolfCrypt libraries, we provide a couple of mechanisms to tie into crypto hardware. At the TLS layer, we support what we call a PK callback, which is like a primary key callback or public key callback, I'm not sure. But when this feature is enabled, it adds a set of APIs that allow you to define a custom callback for each algorithm. So for ECC, there's actually 4 of them. There's a keygen, assign, verify, and a shared secret. And RSA has ones for decrypt and encrypt and sign and verify. And then those callbacks are supported for also Diffie-Hellman, RSA with the PSS padding, which is used for TLS 1.3, and the ed curve 25519. So yeah, I'll go into this some more. Okay, so the crypto dev is something new we added for the TPM support, but it is extensible to any crypto hardware. And when it's enabled, it adds one new API, which allows you to define a callback for crypto operations. And at this time, it only supports RSA and ECC. All right, moving on. So what we're going to show here is an example with the Raspberry Pi and using our Wolf TPM library to talk to an Infineon SLB 9670. So here's example for cloning our repository and building it with the options that our TPM examples use. And of course, all that stuff. And then I provided a couple interesting things here. We have a built-in wolfCrypt test and wolfCrypt benchmark that you can run on any platform once you build it. And then the AutoGen requires some of the libtool and automate things. All right, so our TPM repository is on GitHub here, and this is the latest user manual link. And building it's pretty straightforward. You can clone it and then configure make. And below is a list of some of the options. I feel like it's going off the screen there. Yeah, maybe. But if you were going to build for the ST33, you would add the enable ST33 option. And then if you were using the I2C version of the ST33, you would add the enable I2C. You can see some of the other things here. We have the ability, for example, to build without wolfcrypt, which disables a bunch of features. And then we have an advanced IO, which adds some things like a read-write flag and the actual address that's being used to do an operation against. All right, moving on. So here's some of the examples. So we have a wrapper test that you can run that demonstrates key generation and RSA encrypt decrypt with different padding, and then as well an ECC key gen, sign verify, and a shared secret or ECDH. And then it also shows an example for writing data to the non-volatile memory and reading it back and verifying networks. And then the native tests, we actually have, this is quite extensive when you run it. There's a whole bunch of other things that happen underneath this. If you go to that GitHub repository for wolfTPM, there's a README that shows the output of all of these, and you can see them. And we have examples for benchmark and certificate signing. And then this certgen script is used to, it basically creates a CA and then signs these certificates for testing. So typically what would happen is you create a certificate signing request, and then a CA would sign that, and then you would load that certificate on the TPM. All right, I see a question.
David, we have a question. Will we be able to share the slides following the presentation?
Yes, we will share the slides. So we'll also share a video of this presentation, and the slides I'm happy to share. So that would be handy. All right. So now we're going to talk about the ECC 508A. So I mentioned it before, Microchip has a crypto auth lib, and that same library supports the 508 and the 608A, and it is available on GitHub. Again, we use the PK callbacks for the TLS operations, and we have reference callbacks for those that work out of the box. They've been tested with TLS client side and server side. And then if you define the wolfSSL underscore at ECC 508A, it also makes available the wolfcrypt native APIs, the WC underscore ECC APIs, to be able to use the hardware. There's a comprehensive README at that link there, which is on GitHub. We have some already packaged demos that we did a while back that are on our more downloads page, and then you can also get them from a branch. That's actually, I guess it's a repository that I set up on my GitHub. That's just where they're hosted right now. And then for the ST safe, getting the software is a little more challenging because you have to get it through ST, and they don't publicly put it out there. But assuming you are able to get the hardware and the software, there is a piece that glues it all together. We call it the ST interface layer in crypto configuration code. So we have those pieces, but we're not allowed to put them out publicly, but we can redistribute them with ST's approval. Oh, there's a typo on that. So the same thing here, we have reference PK callbacks for all the TLS operations against the ST safe. We also have a macro, and this is where the typo is, that's wolfSSL underscore ST safe A100 that can be defined to enable the native APIs. And we have a complete README on the GitHub at that link there, which is under wolfcrypt source ports ST. And including, there's also an example API for loading the device certificate. So these, both the at ECC and the ST safe are provisioned with a certificate from the manufacturer.
We have a question. When will on-chip support be available like ARM Trust Zone?
That's a great question. So right now, we don't support it. It has been on a roadmap for about 2 years. We haven't been asked to support it by an actual customer yet. And I think that has to do with the fact that it's not in very much silicon at this time. There is I think one of the Nordic parts is one of the first to have it, the NRF52. we do support the Intel SGX, and we do support the Microsoft Pluton hardware, but those are the only two that we currently support. So the answer to your question is, we're not sure when we'll support it, but hopefully by the end of the year, early next year at the latest. So again, we do offer consulting services and we've definitely quoted it, but we just haven't done it yet. So yeah. All right, so that is actually my last slide. So now I will open it up for all the questions you guys can ask. Stump the engineer.
You can as well, following the presentation, if you have any questions, feel free to send an email to info@wolfSSL, and I will follow up with a link to the recording as well as the slide deck.
Give a few moments, see if anybody types any questions in or raises their hand. Either way, I hope you all enjoyed the presentation.
It looks like somebody's got a question here. Hang on one second. Okay, James, you're unmuted.
So I'll ask this, I'll read this question. So do you have the cost matrix available for ST-Safe and the other chips? The answer is no. We are not privy to the costs for those chips. That's something you'll have to investigate on your own.
Okay, will you distribute the slides? Yes, we will distribute the slides. When using the hardware, or excuse me, when using a hardware TPM, how does the host application authenticate itself to the chip?
Yeah, so they use a mechanism called parameter encryption. And it uses a combinations of things, but there is a key established the first time, and there's some other parameters that are wrapped in as well. It's something that is defined in the TPM specification, and the support is mostly there in our library at this time. So.
Okay, how are the TPM 2.0 and crypto devices different? Just different functionality? Question mark.
Well, one's standardized and the other's not. The crypto devices from ST-Safe and at ECC, that they really only support the elliptical curve, but they achieve the same thing. The TPM 2.0 specification has a whole lot more to it, and it supports a whole lot more features. I mean, this is the kind of thing you use on a desktop PC, right? So it has functionality that's almost too advanced for some of the IoT stuff, which is why we tried to just simplify it with wrappers. There's a whole bunch of stuff on the TPM spec about policies and how you give permissions to certain operations and not. And all of that is much more simplified in the coprocessor cases with ST-Safe and the ECC 508. Yes, you can import keys into the TPM. So the question was, does Wolf TPM support importing keys into TPM? So yes, out of the box, we have support for loading public keys, and there is a way to load private keys as well.
Is TPM 2.0 12C communication vulnerable in any way?
Right, so the question is about the TPM 2.0 I2C communication. So by default, most of the operations are going to be sent in the clear. And to protect that, you would need to use parameter encryption. And only the first parameters are actually allowed to be encrypted. But the way they've designed it, the first parameter is the one that has the sensitive data, typically. So again, by default, if you don't use parameter encryption, then yeah, a lot of that information, such as the computed, pre-master secret, is actually sent in the clear over I2C. But you can encrypt it with the parameter encryption. The same is true for the SPI version. It's no different. And only the ST33 part has the I2C option.
Is there a similar model such as ST-Safe AX00 in the future? Is there any SOP guidance for modification?
I've seen references to a newer ST-Safe model in some of the code, but I don't know. I couldn't find anything about it online. So I believe there is something in the works, but I'm not certain. And I'm not sure what you mean by SOP guidance. I think that maybe refers to how you upgrade, but I'm not sure.
Okay. Firmware update API?
Yes. So you're asking about the previously mentioned firmware update framework that we support?
Yes.
So if you go to our Wolf MKGT GitHub repository, we have an example out there. So it's under the examples directory firmware, and it demonstrates taking a firmware image and signing it, publishing it to a broker, and then it also has another side of it, which is a client piece that shows subscribing to a topic that has that's for firmware updates, that takes down the signed firmware package, verifies the signature, and then shows an example of how you would load it onto Flash. So that whole example is out there under our Wolf MQTT repository. Does that answer the question?
Yes.
Excellent. We still have most of you still on the chat here, so keep asking questions.
We can hang on for a little bit longer, but again, this will be recorded, or is being recorded, and I will follow up with the link to the recording as well as the slides. Here we have a question. Do you have any plan for secure boot implementation?
That's a great question. Yeah, so it's something that we've thought about doing, but we have no solid concrete plan to add at this time. I have a feeling when we do the ARM trust zone implementation, we'll probably provide a secure boot example as well. And to clarify on that, we do have many people using WolfCrypt in a secure boot type scenario, but we don't have any examples for that right now.
Do you have performance data for wolfSSL versus wolfSSL plus hardware crypto?
Yeah, most of the benchmarks that I ran were against the crypto algorithms, but the data you're asking for is the TLS handshakes, or how many sessions you can establish. We call it like connections per second. The answer is I have some data, but I didn't do a very thorough benchmark of wolfSSL TLS sessions with and without hardware. I think that would be very valuable, and I'll make a note about it, and maybe we can follow up.
Can you summarize the main reasons to choose Wolf TPM library versus native TPM APIs?
That's kind of a misleading question. So the Wolf TPM library provides the TPM native APIs plus the wrappers, but traditionally people consume it using the TSS specification, which is also a TCG specification. And like I said, it's quite bloated. It supports a whole bunch of other things that don't really add value, because fundamentally underneath, you're just doing, discrete crypto operations. So the answer is Wolf TPM, it doesn't require any dependencies, so it makes it very portable, right? And ideal for embedded use, meaning you can drop a TPM module into your embedded product and use it. Right now, trying to do that without Wolf TPM, with some of the public domain open source stuff that's out there, it ends up being quite bloated. But that's my opinion, I guess.
Okay, we have another question. Do you have data with a comparison with embed TLS?
Great question. We do. We can send you that. Why don't we get your information? We can send you that.
Okay, well, that brings us to a quarter before the hour. So, oh, one more. What do you mean providing support during secure boot? Can you explain that a bit more?
Yeah, so secure boot is basically a way of verifying that your firmware hasn't been tampered with, right? So you traditionally have a bootloader that computes a hash over your firmware and then compares it to a signed value or something that's known. And the TPMs and the desktops do that. Many embedded products are doing that as well because it adds security, level security, meaning that you're ensured nobody's going to be tampering with it. That's the whole point, I guess, or messing with the firmware. But I guess that's the best I can answer it. Yes. So there's a question, can wolfSSL be used for a TLS client and server simultaneously? And the answer is yes. So the way that works is we have, well, I guess I can go into detail, but the short answer is yes. You can instantiate as many wolfSSL sessions at the same time that utilize hardware. You may have to implement some kind of mutex protection against the physical coprocessor in your PK callback or your cryptodev callback, such as a mutex, but that would be the extent of it.
How is wolfSSL going to add any specific functionality for the secure boot? We currently use hashing, as you mentioned.
So I don't think we have an answer for that. So what we would provide when we do it is basically a reference designed for a secure boot. And it would do something like that, hash and sign, or just something to that effect that verify that the code hasn't been tampered with. That is still in the idea phase. It's not something we have even started to implement. So there's another question about what is the plan for the Amazon FreeRTOS package that we published? So there is a public repository that has, it's under wolfSSL FreeRTOS. wolfSSL/FreeRTOS, I think is what it is. And we have out there the FreeRTOS Classic and the Amazon FreeRTOS, and both have ports for wolfSSL in there. I think we'll continue to keep those ports updated and maintained. And we've been working with Richard Berry, who's the author of FreeRTOS, to try and get those integrated upstream. But that process takes a while. So. A lot of great questions, everyone.
Indeed. How much ROM can be required to just use signature verification functionality of wolfSSL, for example, in bootloader?
It depends on the algorithm. It depends if you're using crypto hardware or not. Let's say it was a software only situation where you're using ECC and you're trying to do a verify on a signature. I believe that you're talking about, well, I'm quoting off the top of my head here, about 20K. And if you were doing it with a coprocessor, you'd probably get that reduced down to less than 10K, maybe even less, quite a bit less than that. So, because you wouldn't need our entire math library underneath. So if you have any additional questions, I just recommend sending them to the info@wolfSSL.com, and we'll make sure they get answered.
Well, thanks everyone for joining. And David, thanks for the information and the presentation.
You're welcome.
Have a great day, everyone.
Yeah, thank you.
Bye-bye.